During this presentation, we have to derive the Lagrangian equation for the simple pendulum. A bob attached to an inextensible string capable of making its to and fro motion about the mean position in a vertical plane is termed as a simple pendulum. In order to get the Lagrangian equation, we need a generalized coordinate. Here theta is the generalized coordinate. Therefore, the Lagrangian equation for the simple pendulum is d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. So, this is equation 1. We know that Lagrangian L equal to T minus V. T is our kinetic energy, V the potential energy. The kinetic energy of the pendulum is T equal to half m L square theta single dot square. In general, the kinetic energy T equal to half m small v square. We know that small v equal to r into omega. A relation connecting linear and angular velocities given by the relation v equal to r omega. Here omega should be replaced by theta dot, r into theta single dot. Theta dot is our theta by t. Omega is the angular velocity. But in our case, r should be replaced by the length of the pendulum, L. Therefore, small v equal to L into theta dot. Now, the kinetic energy T equal to half m into L square theta dot square. The potential energy of the pendulum is capital V mg L into 1 minus cos theta. The value of potential energy capital V in general is mg into h. Instead of h, we have to use L into 1 minus cos theta. See this diagram. At the mean position, the energy possessed by the pendulum is fully kinetic. During its forward journey, the value of kinetic energy decreases, but the potential energy is increased. Once the bob has reached the status of B, that means the maximum displacement is attained, energy at the point B is fully potential. Here potential energy is maximum, but kinetic energy at the point B is 0. The point B is called the classical turning point. Now we may get the difference of height between the mean position and the maximum displacement. The difference of height is represented by h. Here the value of h is nothing but our AC. This is h. With the help of these two positions, we have constructed a triangle C O B. With the help of this triangle, we can get the value of OC as L cos theta, because cos theta equal to adjacent side by hypotenuse. Now the value of AC equal to OA minus OC. The value of OA is L. OC is our L cos theta. If you take L outside as a common term, we can get H equal to L into 1 minus cos theta. Therefore, the potential energy capital V equal to mgL into 1 minus cos theta. Now we can write our Lagrangian. L equal to half m L square theta dot square minus of the value of potential energy is mgL into 1 minus cos theta. Now we have to evaluate the value of dou L by dou theta dot. Dou L by dou theta dot equal to, see this equation, this is the only term which is carrying theta dot. Therefore, m L square theta single dot. This 2 comes forward, 2 to get cancelled. So ml square theta dot. Next we have to find out the value of d by dt of dou L by dou theta dot. D by dt of dou L by dou theta dot equal to m L square theta double dot. Then the final term is dou L by dou theta. We have to find out this value. Dou L by dou theta, which is equal to, see here, the first term is free from theta. This second term is carrying the value of theta. Minus into minus plus. The available term is mgL cos theta. If we differentiate mgL cos theta, we can get minus mgL sin theta. If theta is very small, sin theta equal to theta. Therefore, this is equal to minus mgL into theta. Now we can write our Lagrangian equation, that is d by dt of dou L by dou theta dot d by dt of dou L by dou theta dot minus dou L by dou theta, which is equal to 0. d by dt of dou L by dou theta dot is ml square theta double dot minus dou L by dou theta is minus mgL theta. So minus to minus plus mgL theta, which is equal to 0. This is our Lagrangian equation for the simple pendulum. From equation 2, we can write theta double dot plus g by L into theta equal to 0. See here, all the terms are divided by ml square. Therefore, we can get this equation. This equation is further modified as theta double dot equal to minus g by L into theta. Say this is equation 3. Actually, this is our d square theta by dt square, which is our acceleration. That is equal to minus g by L into this theta is our displacement. Theta is our displacement. Now, in simple harmonic motion, the general formula for acceleration is acceleration equal to minus omega square into displacement. This is the general formula. This is equation 4. Now compare equations 3 and 4. In equation 3, we have had theta double dot is equal to minus g by L into theta. Minus g by L into theta. This is our equation 3. But 4 gives acceleration equal to minus omega square into displacement. This is equation 4. The motion associated with our simple pendulum is simple harmonic. The general equation for acceleration in the case of simple harmonic is minus omega square into displacement. From the equations 3 and 4, we can write this is theta double dot is our acceleration. Left hand side of equation 4 is also acceleration. Right hand side is minus g by L into theta in equation 3. Here theta is the displacement. In equation 4, the right hand side is minus omega square into displacement. Therefore, this term g by L is omega square. Omega square. Therefore, omega square equal to g by L. Then omega equal to g by L inside the root. But omega equal to 2 pi nu equal to 2 pi by t. This is our angular velocity, angle by period. Say this is equation 5. This is equation 6. Using the equations 5 and 6, we get 2 pi by t equal to g by L inside the root. Therefore, t equal to 2 pi into root of L by g. So we arrived the period of oscillation of the simple pendulum with the help of our Lagrangian equation.